Hello, and thank you for watching this video design day presentation on the off-grid community Wi-Fi terminal, created by Team Helios. Let's introduce the team.
I'm Rachel Greenland, majoring in mechanical engineering.
I'm Haibar Malikzai, majoring in mechanical engineering.
I'm Dario Salinas, majoring in electrical engineering.
My name is Petit Izere. I'm majoring in computer engineering.
I'm Mansour Alayan, and I'm a systems engineering major.
I'm Blake Denny, and I'm a mechanical engineering major.
Here is the project poster for Design Day. Everything seen here will be covered in more detail throughout the presentation. Let's start with a bit about our sponsor. Viasat was founded in 1986 with a focus on internet in many different situations. Our sponsor team was comprised of Sarah Shepis, Omar Alam, Raymond Barakat, and Curran Mira. The purpose of this project is to provide wireless internet to out-of-reach communities that have no internet infrastructure. This solution is designed to operate in difficult environments. Due to these constraints, this design is portable, low-cost, rugged, and powered by renewable energy. All of these requirements are packaged into one engineering solution, the off-grid community Wi-Fi terminal. The motivation for this project comes from the desire to help solve a worldwide problem, the lack of access to internet. Some members of Team Helios themselves have lived through times where internet access was nearly impossible to find, which gave the team a unique perspective and therefore motivated the team to create something effective. Let's explore the technical aspects of the design and begin with our system block diagram.
This is the system block diagram. Everything inside the dashed line is contained inside the reps. The solar panels generate power, which is sent to the charge controller. The charge controller converts the power into a voltage and current compatible with the battery. The power can then be used by the inverter, which converts the 12 volts DC from the battery into 110 volts AC. The inverter selected has a 120 volt AC inlet to allow the system to run off of grid power and charge the battery. Connected to the inverter are power supplies to power the components of the cooling system, which is comprised of the microcontroller, temperature sensors, and fans. The system also provides an extra power outlet to allow a device to be connected and powered by the system.
To accommodate our requirements, we have 4 boxes to contain all components. 2 boxes contain the solar panels, 1 contains the community Wi-Fi terminal, and the other is the Renewable Energy Power System. This is the Renewable Energy Power System box, or REPS for short. It houses the solar charge controller, inverter, and battery to guide, convert, and store the power. It has 4 fans controlled by an Arduino to cool the equipment inside. We added filters and 3D printed these fan covers to ensure rain wouldn't get in. On the back wall, you will see the fuses and circuit breakers to cut the circuit in case of a fault. Also attached are the battery disconnect switches connected to the inverter and the solar charge controller. There is also an inlet to the inverter so the system can be powered on the grid if needed, and of course the outlet to power the community Wi-Fi terminal. All green wires are for grounding. This is done through a bolt and a grounding rod on the outside. Silicon was placed between each component and its respective hole to allow no water or dust to enter the box. The solar panel boxes were designed with simplicity in mind. 4 panels are installed on each to allow for an easy 4-person carry. On the bottom one, you can see the latches that hold the lid in place while it is in transport. The Community Wi-Fi Terminal Box, or CWFT for short, stores the internet and phone equipment. Inside the container is foam, which is cut to fit the shape of each component. There's an outlet in the back of the box that connects to the reps, and on the right, a junction box for cords to the satellite dish, phone, and access point.
To better understand the lengths our system could go, a couple of analyses were used. A thermal analysis was conducted to better understand the amount of heat our system was going to produce. This analysis was done for the reps box, including the battery, the inverter, and the solar charge controller. The highest temperatures seen from the study were around 41 degrees Celsius, which was below the standard operating range of all components. The next analysis conducted was the shock test. This test was used to determine whether or not our reps box would endure a significant amount of damage from a 30-inch drop. Observing the image, it can be seen that the reps box would remain intact without much damage. In conclusion, our analysis helped us move forward with determining fan selection and component orientation.
In this section, I will be going over how the electrical components of the system are connected. All fuses and cables used were sized based on NEC requirements. The solar panels are connected to the charge controller is connected to the battery, the inverter is connected to the battery, and connected to the inverter are the power supplies for the cooling system, the output to the CWFT, and the inlet to allow the system to run off of grid power.
Now we are going to talk about the hardware for our system. For the hardware, we have Arduino AT-Mega2560, the particle photon, DHT22 temperature and humidity sensor, waterproof DS18B20 digital temperature sensor, SunFounder 2-channel DC 5 volts relay, micro SD card module, Sanyo Denki fan, PCB board, and this is our printed circuit board schematic drawn using a software called Eagle. This is our PCB board design top layer. This is the PCB board manufactured top layer. This is the PCB board design bottom layer. This is the PCB board manufactured bottom layer.
Temperature sensors monitor the inside of the REPS container. If a temperature goes above 38 degrees Celsius, the corresponding fans will turn on. However, once they are on, the temperature will need to drop below 30 degrees Celsius for the fans to turn off.
This is the pseudocode that also shows the loop at which the threshold will be reached for the fans to switch on and off. These are our included libraries, the pin definitions for DHT22, pin definition for the SD card module, pin definition for the DS18B20, and pin definition for fan.
Requirements verification. Here, our tests show that we were able to produce, distribute, and convert power. Due to budget constraints, our system only had one battery and therefore was only able to run for 26.5 hours instead of the required 38. Due to COVID-19, we were not able to do the next test to see if it could charge within a day. The inverter did not output the required 120 VAC within a 3% tolerance. However, it does output 110 VAC within a tolerance of 3%, which still safely powers our system. The inverter does successfully convert 120 VAC to 14.3 volts, which is within the specified range. With our drop test analysis, we proved that our system would withstand shock well enough to pass this next requirement. All of the other environmental tests were unable to be performed due to COVID-19. Finally, I will talk about a few improvements that could be made to the system. The addition of a second battery would allow the system to meet extended power needs of our customer. Lightweight materials could be used to reduce overall system weight. A reduced capacity inverter of about 500 watts will make the system more cost-effective and reduce total overall weight of the system.
Now, even though the senior design project was an experience in engineering, it was still also a class, and what we learned went beyond the specific field of engineering. For some members of Team Helios, this was our first time really fulfilling the role of an engineer. We learned what goes into research, how to conduct trade studies, how to make an argument for a design, and how to manage a project. We also learned together as a team. We learned how to work with each other and take advantage of our strengths. On the other hand, we of course have our share of weaknesses and obstacles, and we address them together. This project taught us plenty lessons about time. The one that has stuck with us since the beginning is that if we think we're on time, then we're definitely behind schedule. We've also learned how to make best use of our time. Finally, we learned the valuable skill of adaptability in this setting. With the onset of COVID-19, we were given a difficult test, and the team handled the situation with professionalism and tact. To briefly sum up this experience, in the beginning, we agreed upon and set requirements to design a solution to a problem. We created our design about $500 under budget and ahead of schedule. We accumulated a lot of research, conducted a lot of analyses in support of our design choices, and we satisfied those requirements to the best of our ability. And in the end, we nearly assembled a functioning prototype. This concludes Team Helios' presentation on the off-grid community Wi-Fi terminal. Thank you for watching, and don't forget to bear down.